If you've ever played the video game Keep Talking and Nobody Explodes, you know it is the ultimate test of trust and communication. One person looks at a bomb, the other person has the manual, but they can't see each other, and you have to defuse it before the bomb explodes. So naturally we thought, why leave anxiety in the virtual world? Let's build a fully functional, super realistic looking physical version of this game. And that's what we did. But doing this in real life introduces a massive engineering nightmare. In a video game, the bomb randomly generates a new puzzle every time you play it. In real life, a printed manual and wired components can't be generated dynamically each time. If the puzzles don't randomly configure themselves every time you flip the power switch, you'll just memorize it in 2 rounds. So it has to be unique each time. Step 1. It needs to look cool, so we snagged this rugged case from Harbor Freight to act as our chassis. The plan was to split the display onto the top and the bottom of the case. A mix of clues, actions, and some visual effects. But what makes up the puzzles? We need components that give us variable options, things that look complex but are fun to interact with. We're talking LEDs, multicolored wires, knobs, toggle switches, and keypads. The key here is balance. We want electronics that the average person doesn't see every day, but something that you can still figure out without an electrical engineering degree. This is actually pretty tricky. To make this a real game, every puzzle module needs 2 inputs for every action to create multiple possible permutations, a combination of clues that equals a specific action. To solve this problem mathematically, we created 2 input tables and 1 output table. So each table is the same. It has 5 rows and 4 columns. And then all we do is randomly select one of these cells from table 1 and one of the cells from table 2, and that'll generate the output for us. So for example, if we took the second row and we picked 3 volts, that would be a value 3. And the second row, let's say we got a 3 as well, and we randomly pick this one, will be 921. So 3 plus 3 would give us 6. 6 mod 4 will give us 2, so we go to the second row, and 2 will give us 584. So regardless of what you choose, we'll automatically know what the action should be on the output side. I'm not going to BS you. It took me a while to figure out this solution. The smooth part of my brain is still hurting. The microcontroller code is going to have to figure out how to manifest all of this theory into reality. Once the math layout made sense, we jumped onto Fusion 360 to design the faceplates. We did a few test cuts on scrap cardboard, adjusted the tolerances, and then fired up the laser engraver to cut the final panels out of slick, matte black acrylic. This panel has buttons, switches, connectors, wires, as well as the microcontroller and the touch display. Most of the actions happen here too. With everything attached, the components had to be connected to the GPIO pins on the microcontrollers. On the top panel is a confusing looking circuit board we snagged from some device and inserted some LEDs. We added a nice 7-segment display and a loudspeaker. To connect the top panel to the bottom panel, we just ran all the connectors through a ribbon cable. We were missing one major component, dynamite, because according to Hollywood, it's not a bomb unless it's made of TNT.
Steady, you can do this.
So we made these with simple black plastic pipe wrapped in brown paper, and of course, curly red wires. Nothing says imminent peril quite like a curly red wire. But we ran into a logistical problem. I move around a lot and need to get on planes, and walking through airport security with a Pelican case permanently packed with realistic looking dynamite is a fantastic way to get introduced to a federal interrogation dude with latex gloves. So science to the rescue. We glued strong neodymium magnets inside the lid and slapped a metal plate onto the back of the fake dynamite. Now they just snap right into place for gameplay, and they pop off when I need to catch a flight. Without the curly red wires, of course. Purely decorative, 100% TSA-safe? Probably, I think. Yeah, we'll find out soon. With the hardware mounted to the panels and all connected up, it was time for the hard part, making it actually work. We're using a 2-brain system here. The main game master is my favorite, the Raspberry Pi Pico RP2350. The second brain is an ESP32 built right into the smart touchscreen display, which will generate visual clues and actions for the player. To get them talking, we wired up a simple UART connection so they can whisper secret binary codes back and forth between themselves. The whole system is powered by a LiPo battery. It's turned on by this incredibly satisfying physical key switch. Every single time you turn on this key, the code has to instantly scramble the input clues and simultaneously calculate the exact mathematical correct sequence for actions required to disarm it. Using our tables and math formula, it should not be a problem. So I didn't write this. See, I consider myself a highly efficient programmer. Some people call it lazy. I call it resource optimization. I turned to my new AI employee called Anti-Gravity. I literally just explained the game rules to him, how the matrix tables worked, and pasted in the exact GPI pin connections for all the components. Then I told him, write the code and don't make any mistakes or I'll replace you with Claude. Side note here, when you're using AI tools, the best results are often achieved with negative reinforcement and direct threats. And lo and behold, it spit out a script. I flashed it to the Pico and it booted up on the first try. I did the same thing for the ESP32 touch display, gave it the communication protocols, and after a little bit of back and forth feedback to fix some bugs, it worked flawlessly. I literally did not write a single line of code. We are so completely screwed when the robot apocalypse comes. But hey, at least I can tell the youth of today I had a hand in their demise. Spoiled little bastards. Back when I was your age, I had to write code with punch cards and in assembly without a calculator. Okay, where was I? Oh yes, we hooked up the debug terminal to monitor the physical game states and made adjustments to the manual, which was much easier than reprogramming or resoldering. Basically make the document fit the game. We also use this 4-position switch that lets you choose your level of anxiety, anywhere from a 1-minute speed run to a 4-minute slow burn for the Gen Zs. So now, if the timer hits 0, the speaker blasts a devastating explosion sound, but if you get the sequence right, you're the hero. But there's only one real way to test a build like this. Play it repeatedly with friends. We brought in the ultimate QA testers, non-geeks. If a bunch of local friends can figure it out without an engineering degree, the design worked. What started as a crazy what if from a video game turned into one of the most stressful, rewarding, and fun party games we've ever built. If you want to experience the sweaty palms and racing heartbeat for yourself, we're actually taking this exact briefcase bomb to open source this year. Come swing by our table, try your hand at defusing it, and see if you can beat the record. Or just blow up your friends. If you want to see more over-the-top engineering builds like this, hit the subscribe button, smash the like button, let me know in the comments what you'd like to see next. Until next time, stay safe, and remember, always cut the red wire. Or don't. I'm a YouTuber, not a bomb expert. Bye.